Hello and welcome to EPG Pathshala Medical Physics module on Medical Proton Magnetic Resonance Spectroscopy. Today's module will discuss Medical Proton Magnetic Resonance Spectroscopy, the basics. I am Dr. Binston Thomas, consultant radiologist at KIMS Kottayam, Kerala. Introduction. Proton MR spectroscopy is a non-invasive diagnostic test for measuring biochemical changes in tissue, predominantly in the brain. It is an extension of magnetic resonance imaging and depends on magnetic resonance signals of hydrogen nuclei, which are present in very high concentrations in water and to a less extent in lipids. While MRI demonstrates the anatomy, morphology and location of a lesion, MR spectroscopy compares the chemical compositions of normal tissue with abnormal tissue basis, its chemical composition only. While there have been studies using heteronuclei such as phosphorus, sodium, by far the most spectroscopic studies use hydrogen nuclei or the proton because of its high sensitivity and ease of implementation on commercial MRI scanners. Firstly, we will try to understand the hydrogen atom and its use in medical imaging. Then we try to compare MRI with MRS. Thirdly, we try to understand the concept of chemical shift effect, the medical MRS, understanding the spectrum, and to obtain a good spectrum, a few tips and tricks. The atom. The atom is the smallest unit of matter. Every atom is composed of a central nucleus and one or more electrons surrounding the nucleus. The nucleus is made of protons and neutrons and are called nucleons. The protons have a positive electrical charge and the electrons have a negative electrical charge, and the neutrons have no electrical charge on them. If the number of protons and electrons are equal, that atom is electrically neutral. If an atom has an uneven number of electrons and protons, they will develop an overall negative or a positive charge, and then they are called ions. The hydrogen atom is an electrically neutral atom consisting of a single positively charged proton and a single negatively charged electron bound to the nucleus. The hydrogen tends to combine with other atoms to form compounds like water and hydrocarbons, which form the predominant constituents of human body and the fundamental element of magnetic resonance imaging and also magnetic spectroscopy. Then what is the MR active nucleus? The observation that many atomic nuclei spin around its own axis, generating an own magnetic field or magnetic moments. This forms the basis for nuclear magnetic resonance. Only those nuclei with an odd number of protons or nucleons have a magnetic moment. In practice, it is the hydrogen, carbon-13, 19 fluorine and 31 phosphorus that are most commonly studied by NMR spectroscopy. Proton precision. MR active nuclei, when subjected to an external magnetic field, will align in with the magnetic moment. In addition to this, they produce a secondary spin or a wobble, which is called the precession of the nucleus around this static electromagnetic field. The precession path is circular. The Lamar's or the precessional frequency is the rate of precession of the magnetic moment of the proton around the external magnetic field. The frequency of precession is proportional to the strength of the magnetic field, that is B naught. The precessional frequency of a nuclei in a static magnetic field B naught is calculated by the Lamar's equation, which is omega is equal to lambda into B, where omega is the Lamar's frequency in megahertz and lambda is the gyromagnetic ratio in megahertz in Tesla, and B is the strength of the static magnetic field in Tesla. MRI versus MRS. Magnetic resonance imaging, or MRI, demonstrates the anatomy, morphology and the location of a tumor, whereas MR spectroscopy compares the chemical composition of normal tissues with abnormal tissue basis its chemical composition. Acquiring MRI data following slice selection with an RF pulse involves slice encoding, phase encoding and frequency encoding gradients in mutually orthogonal planes. The data is then used to provide a spatial and a positional information to generate an image. While in MRS, the frequency signals acquired is used to identify different chemical compounds corresponding to the chemical shift and not the spatial orientation of the signal. The chemical shift effect. MR spectroscopy is based on chemical shift effect. The frequency of precession of a nucleus is directly proportional to the strength of the magnetic field experienced by it. Now, the electrons around nearby nuclei may either oppose or reinforce the magnetic field experienced by the proton. A shielded proton experiences low electrical field and has a lower resonance frequency than compared to a de-shielded proton, which is called the chemical shift effect. Frequency shift referencing is done by comparing a measured frequency with a standard substance and expressing it in parts per million. As seen by the equation, we see that lambda is equal to lambda of the sample, frequency of the reference, divided by frequency of the reference again. So the difference of frequency divided by the frequency of the reference, where the standard substance could be water, TMS, the tetramethylsilane, or an internal standard like creatinine. Now the frequency difference between various metabolites is only a few hertz following the chemical shift, whereas the resonance frequency is measured in megahertz. Hence, it is important for us to express frequency shift in parts per million, that is 10 raised to 6. For an example, an MR signal observed at a frequency of 300 Hz, higher than the signal of a standard like TMS, where the TMS resonance frequency is 300 MHz. In a frequency shift chart or a graph that represents various metabolites and its resonant frequencies, the nuclei are found to resonate in a wide range to the left of the internal standard. Types of medical MRS. There are many studies using heteronuclei such as phosphorus 31 phosphorus and sodium 11 sodium. By far, the most spectroscopy studies use proton nuclei, which is the hydrogen nuclei, because of its high sensitivity and ease of implementation on commercial MRI scanners. Other reasons include high signal to noise than sodium or phosphorus and ease to perform a proton MRS, around 10 to 15 minutes, and the convenient addition to conventional MRI imaging protocols. Phosphorus MRI. The following is a chart of a spectrum of phosphorus MRS, where we see the internal standard, which is the phosphocreatine, aligned at a 0, and to the right of the internal standard you see ATP, that alpha, beta, gamma ATPs aligned to the right of the internal standard, and to the left of the internal standard you see the phosphorus monoesters and the diesters and the inorganic phosphorus. Now let us discuss the proton MRS spectrum. Let us start with the composition. The proton MRS spectrum predominantly contains water, which resonates at 4.3 to 6 ppm, macromolecules, the lipids, metabolites which are less than 2000 kilodaltons resonating at 0.5 to 4 ppm, metabolites less than 1 millimoles resonating at 6 to 10 ppms. Distribution of metabolites on the proton MRS spectrum. If the entire signal were used for MRS, the fat and water peaks would predominantly overrule all the other metabolic peaks on the graph. And anyway, since we are not interested with fat and water, the fat and water signals must be eliminated. The normal MR spectra obtained from grey matter shows predominantly metabolites displayed from right to left, which include NAA, the creatinine peak, the choline peak and the myo-inositol peak right to left. Now each metabolite appears at a specific ppm and reflects specific cellular and biochemical process. The NAA is a neuronal marker and decreases with neuronal breakdown. The creatinine measures internal energy stores. Choline represents increased cellular turnover and rises in tumors and inflammatory processes. However, many notable metabolites like the DNA, RNA, most proteins, enzymes, phospholipids, neurotransmitters such as acetylcholine, dopamine and serotonin are missing in the brain spectra. This may be due to very low concentrations undetectable to present day techniques. How to obtain a good spectrum? Equipments required. Practically any strength of MR scanner may be used to perform a MR spectroscopy. Signal strength is directly proportional to the square root of magnetic field. So, there is a significant improvement in signal to noise ratio, which is the SNR, as the magnetic field strength is increased. Typically, a 1.5 and 3 Tesla MRI scanners are used for optimum results. Higher the magnetic field, better the peaks are spread across the spectrum and the metabolites can be easily picked up. Here is a chart that compares the spectrum of a 1.5 Tesla and a 3 Tesla magnets. You can see the 3 Tesla magnets show metabolites which are well spread out with sharp peaks. Patient preparation. No specific additional preparation is required beyond that what is used for an MRI examination itself. However, confirmation from a local MRI staff is recommended. Duration of the study. This varies, but most modern MRI systems can perform routine adequate scans in 5 to 15 minutes. Spending time carefully shimming before MRI spectroscopy is very important. This typically is done by routine just before the MR spectroscopy. Post-processing typically is an automated procedure on many modern systems and is commercially available. Steps of acquisition. Firstly, a localizing sequence to identify the area of interest is required, which is generally a T2 or a flare sequence. Post-gadolinium contrast images are used only if absolutely necessary. Use the best sequence where the pathology is best demonstrated. Positioning a voxel, which can be a single or a multi-voxel region of interest. Voxel localization can be done using STEAM, stimulated echo acquisition mode, where low TE acquisitions are possible, or with PRESS, point resolved spectroscopy, which provides high signal to noise ratio and is more popularly used. Voxels can be single or multiple. Single voxel. Single voxel is a small volume that is selected. The voxel size can vary from 1 to 8 ml in practice. Most often between 1 to 2 ml is generally selected. Smaller voxel size gives a better representation of tissue to be characterized, but there is poor SNR if the voxels are increased in size. There is a limited anatomic coverage. Voxel positioning is very critical and the spectral resolution is the best using single voxels. Multiple voxels. Here a large volume is selected which yields spectra from multiple voxels simultaneously. Now the spectral resolution is moderate. MR spectroscopic imaging MRSI, or the chemical shift imaging. Here we can acquire a 2D, a single slice, or a 3D multi-slice image. Here a more anatomical coverage is acquired. Data is presented as a color coded image for each metabolite of interest, which is visually pleasing. A higher grade of shimming is required, and it is especially difficult in posterior fossa lesions where a lot of bone and the compartment is a very small area. Shimming the area of interest. Good shimming is required to correct the magnetic field inhomogeneities prior to obtaining a spectrum. A field homogeneity to the order of 1 ppm over a volume of several liters is needed in an MRI scanner. Water suppression levels checked. This can be done by two methods. One is CHESS, chemical shift selective excitation, most frequently used technique. Water signal is eliminated using one or more 90-degree pre-saturation pulses centered over water resonance frequency. Or we can use a water elimination Fourier transform techniques where a 180-degree pulse is centered over water. This is slightly less efficient than CHESS for water suppression. Now let us examine the effect of TE on the spectrum. Now spectra with long TE shows fewer peaks with due to short T2 of compounds such as lipids which appear smooth. It is better to look at. Spectra which are acquired on a short TE, you see more metabolites but more of overlap, more difficult to distinguish the peaks, and metabolites are always best visualized in the optimal TE. Now here is a list of metabolites that can be visualized on an intermediate to long TE, which is around 144 to 288 microseconds. NAA peaks, the choline peaks, the creat peaks, and the lactate peaks. Using a short TE, time to echo, less than 30 milliseconds, gets us lipids, glutamine, and myoinositol peaks. Display of spectrum. This can be done in a graphical display, amplitude versus frequency, or a chemical shift imaging display, or a spectroscopic imaging display. Images of abundance of the certain metabolite can be picked up. Grayscale or color depiction of metabolites also can be seen. Display of spectrum. The spectrum can be displayed graphically. It can be displayed on an amplitude versus frequency graph, a chemical shift imaging or a spectroscopic imaging where color maps are used, or imaging of abundance of a certain metabolite only can be picked up. Grayscale or a color depiction of a metabolite again can be shown separately as a display. Analysis of a spectrum. There are two ways to analyze. One is the qualitative, the other is the quantitative. In the qualitative, we have visual, the character of the peak, the position of the peaks, the intensity of the peaks, the form, and area, more important than the amplitude. We can also use certain ratios like Na creat ratio, choline creat ratio to analyze these peaks. Spectral resolution, difference in resonance frequency between two molecules, better resolution with the stronger magnets can be obtained. Quantitative analysis. Quantitative analysis is not routinely used in clinical practice. This requires specialized software and post-processing. It is technically more demanding and predominantly used in research faculties. Tips to obtain a good spectrum. Always keep the voxel away from cranium and the skull base. Avoid blood products, air, CSF, fat, necrosis, calcium, metal and bone in the voxel. Obtain internal reference spectrum from the contralateral side, which is always good for comparing. Consider scale factor. If one metabolite predominates, the other peaks appear to be smaller peaks although the concentration is not decreased. Avoid gadolinium if possible, which this may alter the individual peak area. Maintain consistency for follow-up comparisons, because that is very important when it comes to tumor cases on follow-up. So, in summary, MRS is an extension of conventional MRI. It supplements MRI in various aspects. It is based on chemical shift effect. Understanding the various steps helps us acquire a good spectrum for analysis. A good spectrum is an effective problem solving tool in the diagnosis and can help in grading and prognostication of lesions. A good spectrum leads to a happy radiologist and a very healthy patient. Thank you.